Hi everyone, and welcome back to educator.com. In this mini lesson, we're going to go through page 1 of the A+ Physics worksheet on wave-particle duality. And you can find the link to that worksheet down below the video. So let's dive right in. As you do this, you're probably going to need a copy of the electromagnetic spectrum near you in order to answer the questions. So number 1, compared to a photon of red light, a photon of blue light has blue has a greater energy than red light. It has a higher frequency, therefore a higher amount of energy. Number 1. Number 2, exposure to UV radiation can damage skin. Exposure to visible light does not damage the skin. State one possible reason for this difference. UV radiation has more energy because it has a higher frequency. Number 3. Louis de Broglie extended the idea of wave-particle duality to all of nature with his matter-wave equation, lambda equals Planck's constant divided by mass times velocity, where lambda is the particle's wavelength, m is its mass, v is its velocity, and h is Planck's constant. Using this equation, calculate the de Broglie wavelength of a helium nucleus moving with a speed of 2 times 10 to the 6th meters per second. Well, if lambda equals h over mv, that's going to be Planck's constant, 6.63 times 10 to the minus 34, divided by the mass, 6.7 times 10 to the minus 27 kilograms, divided by the velocity, 2 times 10 to the 6th meters per second, is going to give us a wavelength of about 4.95 times 10 to the minus 14 meters. Really, really small wavelength. Number 4. The wavelength of this particle is of the same order of magnitude as which type of electromagnetic radiation? Well, to do that, I need to go to the electromagnetic spectrum, where I find that that is very close into the realm of gamma rays. Number 5. A photon of light carries both energy and momentum. Correct answer there is 3. Photons have energy and momentum, but no mass. Number 6. Wave-particle duality is most apparent in analyzing the motion of small particles. Baseball, space shuttle, galaxy, all big. An electron, small. Most apparent for the electron. Number 7. A photon of which electromagnetic radiation has the most energy? Well, it's going to be the one with the highest frequency. UV, X-ray, infrared, or microwave. I'll use the electromagnetic spectrum diagram to see that that's going to be 2, an X-ray. Number 8. Light of wavelength 5 times 10 to the minus 7 meter consists of photons having what energy? Well, to do this, energy is going to be equal to HF, or hc over lambda, using the wave equation where v equals f lambda and our velocity is c. So that's going to be 6.63 times 10 to the minus 34 times c, the speed of light in a vacuum, 3 times 10 to the 8th meters per second, divided by our wavelength, 5 times 10 to the minus 7 meters, which is going to give us an energy of right about 4 times 10 to the minus 19 joules. Answer number 3. Number 9. Electrons oscillating with a frequency of 2 times 10 to the 10 hertz produce electromagnetic waves. These waves would be classified as, well, if they oscillate with that frequency, the waves that are created would have a frequency of 2 times 10 to the 10 hertz as well. Using the electromagnetic spectrum, I can look and find out that those fall into the range of microwaves. Answer number 3. Number 10. The energy of a photon is inversely proportional to its, well, remember, energy is HF, or HC over lambda. So wavelength, yeah, it's inversely proportional to wavelength. Answer must be number 1. And last question. A photon has a wavelength of 9 times 10 to the minus 10 meter. Calculate the energy of this photon in joules. Well, again, energy is hc over our wavelength, which is going to be 6.63 times 10 to the minus 34, Planck's constant, times the speed of light in a vacuum, 3 times 10 to the 8th meters per second, divided by the wavelength, 9 times 10 to the minus 10 meter. plug that into my calculator, and I come up with something pretty close to 2.2 times 10 to the minus 16 joules. All right, that completes the first page of the worksheet on wave-particle duality. If you struggled with this, probably time to go back and review that lesson in the main portion of our lecture series. If it went great, excellent, time to move on. Thanks so much for your time, everyone, and make it a great day.